My name is Jeff Doyle, and as the slide says here, and my apologies for having company logo kind of plastered up here prominently, I'm the IPv6 Solutions Manager for Juniper Networks. But I'm also a member of and active in the IPv6 Forum and the North America IPv6 Task Force and some other things. And this presentation, I'm really wearing that hat more than a Juniper hat. So we'll look at it in that direction. This presentation, as it says here, is a wide but shallow overview of the protocols and mechanisms and issues surrounding IPv6 deployment. This is a presentation that I put together for Apricot a few months ago in Taipei, and at that time it was about a 4-hour presentation. I was given 90 minutes for this one, so I had to do some radical surgery on the presentation. I'll tell you a little bit about what I took out, just so that you know that those things are out there. Part of it is just maybe the biggest issue of all, which is something that I actually took out of here, is, well, why IPv6? What are the drivers that are out there, and who really cares? You know, is this ever really going to happen? You get different answers in North America than you do, for example, in Asia. Probably a big reason for that is that if you look at the total allocated IPv4 addresses, 74% of them are in North America, 9% are in Asia. And that very much reflects why there's more of a sense of urgency that something needs to be done in Asia than in the US. We sort of have the luxury of sitting back and seeing how successful IPv6 deployment is there before it gets adopted here. So a lot of information about drivers and what's going to happen. I took all that out. Things like my own opinion, which is that IPv6 is really going to be driven by the consumer electronics industry. That's the people that want to have more and more network-enabled devices, and if they know that if they want to keep selling those devices and selling services, they've got to have a better addressing scheme than what's out there now, and more easily available addresses. That's why you see so much interest in IPv6 in places like Japan, in Taiwan, and South Korea, increasingly in China, because those are all countries where they have large consumer electronics industries. That's a lot of where that driver is going to come from. A couple of other things that I took out, probably major topics, are routing IPv6, which makes me kind of sad because I'm a router guy, and that's what I like talking about. But I can tell you very quickly there, without going into any of the details, that all of the routing protocols that are available for IPv4 are available for IPv6 also, with some modification. You have RIP-NG, you have OSPF v3 for IPv6, you have ISIS, which has some you throw in a couple of extra TLVs and ISIS is ready to go for IPv6. Multi-protocol BGP supports IPv6 and so forth. So all of those things are there. Is anybody here from Cisco? Does EIGRP support IPv6? I don't know. I don't think it does, but it's the other kind of major routing protocol out there. Yes, sir? I heard a rumor that it never will. Never will? Yeah, I don't know for sure, so I didn't want to speak for something I'm not sure about. But anyway, with the probable exception of EIGRP, all of the major routing protocols are available for IPv6. The other big issue that I chopped out of here is multi-homing. There is a lot of meat there, and in these slides that I guess are going to be available on the web, is that correct? They're there now. I actually stuck all my multi-homing slides in at the very end, just because it's an important enough topic that even though I don't have enough time to talk about it today, I wanted you to have that. And if you find this presentation useful, what I might do is propose to Susan that I do a multi-homing IPv6 talk in Chicago later in the year, and we'll get to those subjects. So, a wide, but not quite as wide as it was originally intended, presentation of some of these issues. What's really left is mostly talking about transition mechanisms and transition tools. And shallow because I could probably spend 90 minutes talking about any one of the many tools that I'm going to talk about in here. So it's just sort of a little taste of each. The other thing I'd like to say before I really get going on all of this is that I know there's a few people here that know a lot. I see a few faces here that know a lot about IPv6. Please feel free to jump in at any point in this if you have something to add about anything that's being talked about, or if you find that I'm saying something incorrect, please, I have a pretty thick skin, so please feel free to correct me about those things. So, an assumption here is that you already understand the basics of IPv6. You understand address structures, you understand the dynamics of address auto-configuration and ICMP v6, extension headers, and so forth. I'm not going into any of that stuff. If you don't know these things, it doesn't matter that much. I think you'll still get something out of what's here. And then just a quick slide talking about IPv6 features. What's different about IPv6? And of course, the big difference is that rather than a 32-bit address space, you've got a 128-bit address space, which means you have an exponentially larger number of available addresses. And I've sort of written that up there. 128 bits means 340 trillion addresses, which I've also got written out, if you really care, right there. And one of those little, kinds of trivia things that I found somewhere, I don't remember where I found it, shows that this works out to about 67 billion addresses per square centimeter of the planet. So there's a lot of addresses there. And one of the slides, by the way, that I've taken out is something that injects a little more reality into that. There's not really that many addresses. But there are, nonetheless, a lot of addresses. And that's really the primary driver for IPv6. Aside from everything else, it's just a bigger address space. And that's the only real reason for adopting IPv6. Some other features, it has a hierarchical address structure. Well, so does IPv4, but the hierarchy is a little more rigid with IPv6, which means that address aggregation should be better with IPv6 than with IPv4. It has a more efficient header architecture. The basic IPv6 header is simpler, even though it's a bit bigger than IPv4, it's simpler than IPv4, which could make a difference in particularly some smaller software-based routers. It should improve forwarding performance a bit. Neighbor discovery and auto configuration. Next to the larger address space, that's probably the biggest attractive feature of IPv6. It has some very definite implications for mobile IP, because mobile devices can much more easily acquire care of addresses with IPv6 than they can with IPv4. It also could mean some improved operational efficiency, particularly things like network renumbering and the such. Could be easier because of address auto-configuration. And finally, there are some integrated security features, particularly authentication and encryption, IPsec, are built in to IPv6, whereas they're just add-ons with IPv4. That means that security should be somewhat easier with IPv6. I've seen several different presentations and read several different articles that say that IPv6 is more secure than IPv4, and that's not true at all. It's no more secure than IPv4 is. What is different is that security is a bit easier because the functions that you want for security are built in. This becomes particularly important when in the section that I took out about motivating factors for IPv6, you talk about things like peer-to-peer networking and the increased importance of that and how IPv6 could make peer-to-peer easier. And when they start talking about, as I will talk about, eliminating NAT, end-to-end security becomes much more important because you can become much more visible if you start restoring the globally unique address model that the internet was originally supposed to have. So that is the one driver that I've left in here that I do want to talk just a bit about. is the fact that, as I said early on, the primary and only real motivation for IPv6 is more IP addresses. IPv4 addresses are, as I also said earlier, are becoming particularly scarce in Asia. You've probably all heard the story that Stanford University has more IPv4 address space than the entire country of China. That's actually not true anymore, but it was true until a year or 2 years ago. That's a pretty significant statistic. That didn't happen out of any maliciousness or anything. It just happened back in the days when everybody thought that the ARPANET and such was never going to grow to anything big, and people involved in that took very big blocks of addresses, thinking there was just a more or less inexhaustible supply of IPv4 addresses. The imminent demise of IPv4 has been predicted since about the mid-1990s. You've probably also seen all of those articles around, in 1994, 95, that showed graphs of the increased allocation of IPv4 addresses, and pretty much all of them would say, at this rate, if it continues for another 2 years or whatever, we're going to be out of IPv4 addresses. Well, there were 2 initiatives that were taken to stop that address depletion. The long-term initiative, originally called IP Next Generation, IPNG, and eventually became IPv6, was sort of the permanent solution, at least until IPv6 itself starts having problems with address depletion. But that takes time to develop. So the short-term solution was network address translation and dynamic IP addresses, RFC 1918 addresses. That was always intended as just a short-term solution, something that will slow address depletion until the next generation of IP is ready to go. But that solution has become so popular that there are now a lot of people that question whether we ever will need IPv6. They're warm and happy behind their NAT boxes. And the statistic that I have here shows that some 70% of Fortune 1000 companies currently are using NAT. So the question is, why not just continue with what we're doing? And I put down here kind of a big red but. NAT causes problems on the internet, and I'm sure there's probably not a person in this room that doesn't understand that and know that. Specifically, it addresses, it can break or does break the globally unique address model that the internet was always kind of intended to have. It breaks address stability, and this next bullet point really kind of says the same thing. It breaks the always-on model, because if you have dynamic IP addresses, an address that a device has one day may not be the same address that a device has the next day. It breaks the peer-to-peer model. And again, some of the stuff I cut out of this, I talk a lot about peer-to-peer and some of the things that's happening with peer-to-peer and grid networking and or grid computing and all of that sort of thing in the internet now. NAT is a big barrier to developing those kind of new applications. It breaks some applications, particularly security and quality of service types of applications. Anything where you have to take your IP address and include it somewhere at the application layer. If your packet goes through a NAT box and the address in the header changes and no longer matches the address that's in the application, then that application can break. It introduces a false sense of security. There's a lot of people that consider NAT to be a part of their security scheme, and that NAT does a great job of kind of hiding their network. Well, it can have some security implications, but not nearly as much as people think. NAT itself does not make you tremendously secure, hence a false sense of security. And then finally, NAT introduces some hidden costs. It introduces administrative costs in your network, simply having to deal with NAT. It introduces very hidden costs in application development, when application developers are having to consider how do I make my application work through a NAT box, because there's so much NAT out there, particularly in homes, in small businesses and the such. There's NAT boxes. How do I get around that? So NAT becomes a big barrier there to application development. NAT also becomes a big barrier to development of new kinds of applications. Many application developers will say that that's sort of the big hindrance right now in looking at new ways to use the internet and new services and applications that can go over the internet. And that's a problem. So IPv6, because it has plentiful global addresses, means no more NAT. And again, as I said earlier, doing away with NAT also means that end-to-end security becomes much more important, because you don't have that hidden element, and security should be better with IPv6 than with IPv4, because you've gotten rid of NAT and done security the way it really should be done. Some transition assumptions. One of the big assumptions, and there's some mythology around this, is that there will be no flag day with IPv6. I still see articles in the media on a regular basis that say, well, the big reason IPv6 isn't being adapted is that it really scares people with the idea of just shutting off IPv4 and turning on IPv6. Well, that's not going to happen. It's never going to happen that way. The last time we had in the internet a flag day type of transition was in 1983, specifically January 1st of 1983, when we transitioned from NCP to TCP. And it's something of a famous disaster. Didn't happen anywhere near as smoothly as people had planned, and it was a lesson learned. It's something that just won't happen again. Transition will be incremental. If you're talking about an enterprise, a large enterprise, you should probably be looking at transition happening over some number of years. If you're talking about the internet itself, more than likely transition is going to happen over a decade or so. It's not something that's going to happen overnight. There shouldn't be any IPv4 and IPv6 barriers at any time. In other words, there should be smooth communication. There should never be a point where an IPv6 device can't talk to an IPv4 device and vice versa. And that's a big part of what we're going to be talking about with transition mechanisms. It should be easy for the end user. If you switch from an IPv4 only device to a dual stacked device, it shouldn't break any kind of applications. For the end user, they should, end users don't really care, don't even know what IP is usually. They just want to see their applications working, and it should, all of that decision making of whether to use IPv4 or IPv6 in a dual stacked device should happen behind the scenes with no visibility to the user. And IPv6 is designed with transition in mind. A good way to think of the transition is not transition itself, but coexistence, at least for the short term. My own opinion, I guess I should say that IPv6 is really designed with the idea that it will always need to coexist with IPv4. My own opinion is that once IPv6 really takes off, I think you'll see IPv4 die off pretty quickly within a matter of just a few years. But nonetheless, it's a good decision, and it's a good way to look at it, that these two things need to always coexist. There are a lot of different transition technologies, which you'll see in this presentation, and that's a good thing because there's a lot of different kinds of networks, there's a lot of different kinds of networking philosophies, and so the more tools you have in your toolbox for doing these transitions, the better. For some transition strategies, a couple of different approaches. One is edge to core, and that's really what it seems like most people focus on. Is edge to core. That can be important when IPv6 types of services are being offered to customers. Speaking from an ISP standpoint, when addresses are scarce at the edge and you want to start servicing more customers, it can be good to transition at the edge. And that's usually going to be user or customer driven. Probably another example of something you might see driving IPv6 adoption from the edge, from the users, is online gaming. Already, most of the gaming manufacturers, Sony and Microsoft and Nintendo, the big three kind of in there, are looking at peer-to-peer online gaming and how that improves the performance of gaming. IPv6 can be a big element in that, and that could be the kind of thing that starts driving transition from the edge when users start saying, I hear that IPv6 based peer-to-peer online gaming has much better performance than server-based gaming. Why can't I get that? You know, speaking to their ISPs. And that gives the ISPs now a business case for starting to transition.
Well, you're assuming that somebody's going to pay for online gaming.
Pardon?
You're assuming someone's going to pay for online gaming.
Yeah, for sure. Yeah, I mean, there's all kinds of models there. You know, it's an online, peer-to-peer online gaming model is probably still going to have a server element in there. You know, where you go to a server to find an opponent and to do whatever financial transactions that you need, you know, and then to actually play the game, you switch to peer-to-peer. That's one model that could happen. You know, other things could be just that, you know, the cost of that could be built into the games that are sold. I don't know that part. The edge-to-core transition, though, to do that really means probably tunneling technologies. So that if you still have an IPv4 only core, you've got to tunnel your IPv6 through there, which means increased administrative costs and so forth. So for some ISPs that are simply preparing themselves and getting ready to start offering IPv6 services, core to edge transition may be a better strategy. If you don't have immediate customer demand, you're simply wanting to get ready for that customer demand, starting to dual stack your routers from the core out. Could be a good strategy, and by dual stacking, you've avoided a lot of administrative overhead associated with tunneling. If you start talking about enterprises, you know, it's something I just threw in there. I've actually never actually looked closely at what the vulnerabilities are and such, but you perhaps transitioning by routing protocol area. Could be a good strategy. Enterprises tend to look at their networks more in terms of areas than, you know, cores and edges like an ISP would. You could probably transition by subnet, but I think that's probably quite a bit too incremental. There's three types of transition mechanisms. There's dual stacks, there's tunnels, and there's translators. And I've listed those probably in the order, how do I want to say that, in decreasing order of desirability. In other words, the best way to transition, if you can, would simply be to dual stack everything. Let your routers, let your host devices simply talk IPv6 when DNS gives them an IPv6 address, talk IPv4 when DNS gives them an IPv4 address. And you know, there's relatively little administrative overhead with that, and works well. All the major router vendors support IPv6 right now. All of the major operating systems in devices support IPv6. Microsoft has it, Apple has it, all the various flavors of Unix, most of the various flavors of Unix have it. So it's all there and it's all available for doing dual stacking. When you do have to separate networks into different parts where you've got just v4 only portions of your network, then tunneling becomes an important transition technology. As it says here, for tunneling right now, IPv6 over IPv4 clouds, and as you sort of move further along into a world where it's mostly IPv6, then you want to be able to tunnel IPv4 over IPv6 clouds. So tunneling is really so that v6 can talk to v6 and v4 can talk to v4. When you need for a v6 only device to talk to a v4 only device, you need translators. And that's probably the least desirable and most administratively burdensome transition technology to use. It's something that you probably want to try to avoid unless you just have areas where there's no other solution. And we'll look at each one of those in quite some depth. The first thing is dual stacks. Dual stacks is maybe kind of an unfortunate name, and it implies something like this, where you have IPv6 applications that work all the way down a stack, and you have IPv4 applications that work all the way down a stack. This is not something that's really desirable. What you really want is dual layers. So even though they probably still call this dual stack, what you want is, at least in the application layer, applications that are agnostic to IPv4 or IPv6. Again, if DNS returns an IPv6 address, then we'll talk IPv6. If DNS returns an IPv4 address, we talk IPv4. That's more what you really want in a dual stack, is applications that don't care what's below it, or either don't care or are capable of using either v4 or v6. Then we get into tunnels. There's three different ways of looking at tunnels, or three different tunnel applications. There's router-to-router tunnels, which is shown in this top illustration here, host-to-host tunnels, and router-to-host and host-to-router tunnels. And we'll look at applications of each of those. The particular tunnel types, and I'm sure there's more out there, listed here are the ones that I know about. There's, first of all, configured tunnels. This is something that's going to be used in a network core, where you simply set up a tunnel and it's expected to just stay there all the time. Those are always going to be router to router. There's also automatic tunnels, and there's a whole list here, and there's references for each one where references exist. Tunnel brokers, 6-to-4, ISATAP, however you want to say that, 6/4, Teredo, IPv6-4, and DSTM. And I'm going to talk about each one of those. So the first couple of examples are configured tunnels. This example here just shows a GRE tunnel that is configured to carry IPv6. In this particular case, I've got a Junos configuration up here. You can do the exact same thing with Cisco iOS. You can do it with Hitachi. You can do it with other router vendors. It's a common configuration, and it's a pretty easy to understand configuration. If you've ever done any kind of tunnel before, then you can see there's simply tunnel sources and destinations that is relative to the IPv4 side that sets up the tunnel endpoints. And then from the IPv6 side, the tunnel is viewed as an interface. And you can see down here we've got an IPv6 address applied to this tunnel that becomes the tunnel interface. You can also use MPLS, and again, I've got a kind of a brain-dead Junos configuration. It's a very abbreviated configuration up there, but you can do the same thing with Cisco. I'm pretty sure you can do the same thing with Hitachi. If you have an MPLS-enabled core, then you've already got a nice transition technology in place. You can simply tunnel your IPv6 traffic over MPLS LSPs. So two examples of configured tunnels, again, to be used in the core of networks, usually for tunneling IPv6 edges through an IPv4 cloud. Very quickly, I wanted to talk about the tunnel setup protocol, which is not a specific IPv6 transition technology, but it's used by a couple of transition technologies. As it says here, it's a proposed protocol that's a control protocol for setting up tunnels, or particularly for negotiating tunnel parameters. As I already said, it is used by a couple of different IPv6 transition schemes. It can negotiate actually either IPv6 or IPv4 tunnels, and it actually uses XML messages over a TCP session. The kinds of tunnel parameters it can negotiate, or some of the parameters are shown here: IP addresses, prefix information, tunnel endpoints, of course, a DNS delegation, and other things. And there's three phases to TSP. There's an authentication phase, then there's a command phase, which is from the client to the server. In other words, send a command saying I need to set up a tunnel. There's the response phase, which is traffic going from the server back to the client, providing tunnel setup information. So just wanted to cover that because I'll make some references as we go through a couple of different technologies to TSP or tunnel setup protocol. The first tunneling technology that I want to talk about for automatic tunnels is a tunnel broker, which is described in RFC 3053. That RFC gives a general architecture, not a specific protocol framework. It's just an architecture. Tunnel brokers are designed so that individual devices or small sites can connect to an existing IPv6 network. And there's three basic components. There's the client, which is just the device that wants to connect, and it's going to be a dual stacked device, either a host or a router. There's the tunnel broker itself, which is a server that does the actual negotiation of the tunnel parameters. And then there's the tunnel server, which is actually a router. It's a dual stacked router that is connected somewhere to an IPv6 network and provides the other endpoint. Of course, the client is one endpoint of the tunnel, and the router becomes the other endpoint. I've also listed here a few existing tunnel brokers. If you do just a Google search on tunnel brokers, you'll find some sites that give you long lists of tunnel brokers that exist out there. Here's a few of them. And here's a bit about how the tunnel broker works. You can see here we've got a client. Over here is the tunnel server, which again is just some dual stack router that has connectivity to an IPv6 network. And then kind of a conflict in terms here, but the tunnel broker, which is actually a server. And then you can also see there's DNS out here. Yes?
If you're starting out and you're building little stacks and all of your upstream providers are IPv4, can you determine where the best place is to drop your tunnel for your V6 traffic?
I think are you talking specifically for tunnel brokers or just whatever kind of tunnel?
Probably more router to router.
Yeah.
Just as you begin the transition and the providers around you haven't started V6 connectivity or BGP.
I think it would just really depend on where your point of connectivity is going to be to V6. Whether you're talking about connecting to Abilene or whatever, and from there it's just a matter of looking at what's your shortest path for doing the tunnel. I don't have a real specific answer to that, but probably just looking at shortest path for getting to your IPv6 connectivity. Okay, just a few steps here on tunnel brokers setting up. First thing that happens is the client is going to authenticate to the tunnel broker. It then sends a configuration request. I need a tunnel for this particular destination. The tunnel broker decides, and I don't think this is really answering your question, but here's an example of the tunnel broker itself deciding what's the best tunnel server to use. It chooses the IPv6 addresses. It also chooses a tunnel lifetime. How long is this tunnel going to remain up? It then registers the IPv6 addresses in DNS. It then sends the configuration info to the tunnel server and to the client. So now the router or tunnel server and the client have the information they need they know they will be tunnel endpoints, and they have the information they need to set up the tunnel, and at that point the tunnel gets set up. 6-to-4 is another automatic tunneling technology, and this tunneling technology is used for mostly site-to-site tunnels. If you have IPv6 sites that need to connect over IPv4, 6-to-4 is designed for that. It can also be used for connecting a site to the larger IPv6 internet, if you want to call it that, through things called 6-to-4 relays, and I'll talk about those in a moment. A site border router with 6-to-4, or if you want to say it that way, a 6-to-4 router, has to have at least one globally unique IPv4 address that it will use for identifying tunnels. And it embeds that IPv4 address in an IPv6 address. An example is shown here. there is a reserved TLA, which is the first 16 bits of the IPv6 address, which is 2002, and that's a reserved 6-to-4 prefix. Into that, it adds, right after that, it adds its IPv4 address. And an example is shown here. We've got 138.14.85.210. If you change that into hex, you get this. And as a result, the 6-to-4 prefix using this IPv4 address is shown here, and you have this 48-bit prefix. The 6-to-4 router then advertises the 6-to-4 prefix to hosts using router advertisements. And as it says here, that embedded IPv4 address allows discovery of tunnel endpoints. And here's just sort of a simple example shown here of a 6-to-4 setup. You can see that it could be site to site, as shown here, say within a particular enterprise or something like that. Or using a 6-to-4 relay router, it can provide connectivity out to the public internet. And you can see here these two 6-to-4 routers. I've shown the IPv4 addresses that I just kind of made up. There's no significance to those. And the resulting 6-to-4 prefixes that are advertised via router advertisements to end users or end devices, which then, of course, add their own interface ID to that to come up with a complete address. I don't really have any discussion in that. Again, this is sort of a shallow coverage of all of these things, but there's a big issue in 6-to-4 as far as multi-homing with 6-to-4 relay routers. That tends to get very complex, and in the RFC for 6-to-4, it talks a bit about that. There are some issues around the kind of increasing complexity of trying to multi-home 6-to-4 relay routers. And here's an example that I actually took off of this PC here when it was connected to, an Abilene network, or an offshoot of Abilene. You can see the 6-to-4 tunneling pseudo interface. Again, this is Windows XP. Here you can see the 6-to-4 prefix, and here in hex is this 65.114.168.91 address that's added. So when you enable IPv6 in Windows XP, it'll automatically create a 6-to-4 pseudo interface in your PC. Another transition automatic tunneling protocol is ISATAP or ISATAP. I never know which way is the best to pronounce that. I've heard it pronounced both ways. This is used more for connecting individual devices across an IPv4 network. In the specifications in the internet draft for ISATAP, it really focuses on connecting PCs to routers. It doesn't discuss it directly, but I see no reason why it couldn't also be used to directly connect PC to PC. There's really nothing in ISATAP that would prevent that, I suppose. It also uses a specialized address. It creates the 64-bit interface ID by using a reserved identifier shown here, which is zeros in then 5EFE. So it's 16 bits of zeros and 5EFE to get this 32-bit reserved identifier. And then the last 32 bits is an embedded IPv4 address. So for example, down here, if you have this IPv4 address assigned on your device, and somewhere out there you have a global IPv6 prefix, which I've shown here. Link local address can, of course, be made from that because you have reserved link local headers. So you just add in the FE80 to that, and you now have a link local address. Once you acquire your global IPv6 address, then you can add your 64-bit interface ID, ISATAP interface ID, to your global prefix to come up with the global IPv6 address. There's a little bit of a chicken and egg thing here that you may have noticed, which is that ISATAP, as I said, is used for connecting a host across an IPv4 network to a dual stacked router somewhere. But I've sort of said here, you've got this global IPv6 address, and in the IPv6 mechanisms, if you have an IPv6 network, the router is sending router advertisements, and that's how this global address or this global prefix is discovered. Well, if you don't have yet a tunnel to your router, how do you acquire that IPv6 address? And the answer is that ISATAP sort of has its own mechanisms behind that for doing router advertisements, a specialized kind of router advertisement over IPv4. And just a little illustration here showing where ISATAP could be used. Like I said, I see no reason with ISATAP that you couldn't use it to connect two IPv6 devices directly over an IPv4 cloud. Or can be used to tunnel, and the kind of standard way it would be used to tunnel is to a dual stacked router, which could be either shown here, or it could go to a 6-to-4 router, which then sets up a 6-to-4 tunnel getting across some other segment of an IPv4 cloud. And here is, again, an example taken from my PC when it was connected to a network, again with Windows XP. If you enable IPv6, you get automatically what they call an automatic tunneling pseudo interface. It's an ISATAP interface. And here you can see I've got a link local address. Here's the ISATAP identifier, and here's the IPv4 address embedded in that link local address. There's also, there was an early automatic tunneling solution called 6/4, sometimes called virtual Ethernet. This was proposed early on, and I've got it here just more for mention than anything else. It hasn't gained much acceptance and is likely to die out completely, mainly because for this solution to work, it assumes that the underlying IPv4 network is multicast enabled, and that's not usually a good assumption. Might be a good assumption in some enterprises, but on a broader scale, not so much. So other than reading through the internet draft for this, you know, there's not much I really have to say about it. But Teredo is something that's really interesting. This is coming out of Microsoft, and this is a pretty nice new transition technology that's very specialized. Everything that you saw up to now, you notice that it somehow involved IPv4 addresses. And as a result, a lot of those kinds of transition technologies will not work through a NAT device. Teredo is designed specifically to operate an IPv6 tunnel through a NAT device. And it does that by simply avoiding creating a tunnel at the network layer. It actually tunnels IPv6 using UDP. In its early embodiments, however you want to say that, it was called shipworm. A Teredo is a shipworm, which is actually not a worm, it's a mollusk. And there's a picture of it over here, Teredo nivalis. And when I put together this slide, I wanted to be clever and put a little picture of a shipworm up here. So I went searching out on the internet, trying to find a picture. And learned a little bit about Teredos, or shipworms, in the meantime. These are incredibly destructive creatures. There was all kinds of pictures of piers that had collapsed into bays and things like that, and ships that had actually sunk as a result of the work of shipworms, which makes me wonder just how wise it was for Microsoft to want to call their proposed solution a shipworm after something that's apparently these things can tunnel through wood up to about 3 feet, and they're just amazingly destructive. So, nonetheless, as I said, it's for tunneling V6 through one or even several NATs, and it can be either stateless or using TSP can be stateful. It tunnels over UDP using a reserve port of 3544 rather than IP, as I already said. The basic components are these. There's a Teredo client, which is just your dual stacked node. There's a Teredo server, which provides the connectivity information for the tunnels. And there's a Teredo relay, which is a dual stack router that understands Teredo. There's a thing called a Teredo bubble, which is actually just an empty IPv6 packet that's used for creating state inside the NAT device. And there's a thing called the Teredo service prefix, which is a prefix originated by the Teredo server for creating the client IPv6 address. And we'll see how all that works together. And I've been trying this out, actually, Teredo, through a little application that Microsoft put together called 3 Degrees, which somebody at Microsoft just described that as Internet Messenger on steroids. It's a cute little application. It's a V6 only application, but it uses Teredo, and that was the main thing I was interested in. I've actually done some instant messaging using 3 Degrees with someone from CANet from my home office, which is behind a NAT device, and it works great. It goes right through the NAT, no problems. So something to play around with if you want, if you have Windows XP. Here's how Teredo works. You can see here we've got a client, and my apologies to those of you in the back of the room. This is a really small type here. We've got a client, and of course IPv4 network. Here's IPv6 network out here. Teredo relay, which is just a dual stack router connecting the v4 and v6 network. Here's our Teredo server. Here's a NAT device with inside and outside addresses. The client has an inside address of 10.0.0.2. The client has discovered the Teredo server and sends a router solicitation to the server. And you can see here's the source address of this client. Here's the destination of this Teredo server. Its address is 1.2.3.4 in this example, and you'll notice it's got a UDP port of 3544, which is for Teredo. The NAT device does its translation. The source is translated to this outside address, and a big part of this whole process here is so that this client can discover what its outside address is when it gets translated. So, the NAT does its mapping. The Teredo server receiving this router solicitation notes the source address and port and the NAT type. It's important to know with Teredo that it doesn't work with some early types of NAT. 3 Degrees that I was just talking about. I have talked to some people who said they've used it and it wouldn't work through the particular NAT that they had. So there's various NAT types. The Teredo server makes a note of what that NAT type is. The server then sends a router advertisement back to the client that contains the service prefix and the origin indication. You can see here's the source and destination address going back to the client that's in the packet. But then it also includes its IPv6 prefix, and you'll notice it has its IPv4 address, if you look closely here, kind of embedded into this prefix. There's also an origin indication, which is what is telling the client what its outside address is going to be, which in this case is 9.0.0.1. The client makes note of that, and it's been a while since I've read the Teredo specs, so I can't talk much about how it obfuscates the origin indication, but it does. And this is shown here. I took this right out of the internet draft for Teredo. So the origin indication is actually included now in the client address, where it's using the server prefix that it's been given, plus this obfuscated origin indication. And then at that point, and by the way, something that's kind of left out of here, obviously, is the tunnel endpoints is also returned. And then it sets up the UDP tunnel to the Teredo relay. And as I've said, I've used this some, and it actually works quite nicely. TSP can also be used here in place of router solicitations and router advertisements if you want a stateful tunnel, and particularly if you want authentication, and you should always want authentication. Moving on to a couple of things that I pretty much just gleaned from various RFCs or internet drafts. Haven't seen these in use much, but I wanted to at least talk about them a bit. The first is a thing called IPv6-4. This is something that's really intended to be used as kind of at a mid-transition point where there's a lot of IPv6 and still a lot of IPv4, and allows packets to somewhat commingle or coexist. It identifies itself as an IPv6-4 packet by using the last bit in the datagram ID of an IPv4 header. And you can see here you've got an IPv6 header encapsulated behind an IPv4 header. So it's a tunnel. And this thing together is called an IPv6-4 packet. When that last bit, which is otherwise unused, is set to 1, it's IPv6-4. If it's 0, then it's just IPv4. There are, in this IPv6-4 scheme, 3 kinds of routers. There's an IPv6 only router, there's an IPv4 only router, and then there are IPv6-4 routers that actually understand this scheme. And they're listed here how they work. You can see the IPv6-4 routers will process 6.4 packets as IPv6. It processes IPv4 packets as IPv4, and then IPv6 only packets, of course, are handled as IPv6 also. Again, because the 6.4 routers know to look at this bit here and process accordingly. IPv4 routers are going to simply ignore this bit. All they see is the v4 header, and as a result, they just treat an IPv6-4 packet as an IPv4 packet. IPv6 routers cannot process IPv6-4 packets because, again, they're going to see just this IPv4 header. So as a result, there needs to be some kind of translation that takes place and does take place in the IPv6-4 routers before they get to v6 only routers. And with that, there is a proposed IPv6 extension header when this translation takes place that an IPv6-4 router can take the IPv4 information and put it into this extension header to carry across the v6 network in case at some other point a v6 router needs to translate this thing back into an IPv6-4 packet. And then the last of the tunneling mechanisms here is dual stack transition mechanism, or DSTM, which is kind of unfortunately named because it doesn't really have a lot to do with dual stacking. It's a tunnel mechanism. It's sometimes called 4/6, and as that name might imply, this is actually something that may be useful, or some later generation of this concept will be useful when we get to the point where we have mostly IPv6, but we still need, mostly IPv6, but we still need to tunnel IPv4 occasionally across IPv6. So this is actually for tunneling IPv4 over IPv6. There are 3 basic components. There's a tunnel endpoint, which is just a border router, a dual stack border router. There's the DSTM clients, which is the other end of the tunnel. And then there's a DSTM address server. You'll kind of notice sort of a consistent feature of a lot of these automatic tunneling processes or mechanisms is that there's a server involved somewhere along there. And that's true for DSTM also, which allocates the IPv4 addresses to the clients. It uses existing protocols to communicate using DHCP v6 or tunnel setup protocol. And the server can optionally assign a port range for the IPv6 or IPv4 addresses, which is very much a NAT-like functionality. And just a real quick, simple view here of what's going on. We've got this client on an IPv6 network with the DSTM server and a dual stacked router, which is the tunnel endpoint. The client needs to reach an IPv4 address. It's gotten a DNS query back that shows a v4 address that needs to be reached. So it goes to the DSTM server, requests tunnel information. The DSTM server then distributes the necessary v4 tunnel endpoint information to both the router and to the client, and then the tunnel is set up. And again, this is v4 and v6. So those are the tunneling protocols, or tunneling mechanisms, kind of the major ones. I think there's probably others out there that have been proposed over the years, but those are the ones that you're likely to encounter. I'd like to talk just really briefly about translators, and I may go through this part kind of quickly, both because for a lot of these translators, I know a little bit less than I do about tunneling protocols. Kind of the further you move away from routing, the less I know. But I want to at least cover them but then I want to get to the final issues on DNS and some other things there. But there's 3 different types of translators that are out there that are proposed right now. There's network level translators. These are the ones that are mostly in use right now, which includes SIT, includes NATPT, and includes a thing called bump in the stack. There's transport level translators, TRT is the example I'm going to show, and then application level translators, bump in the API, SOC 64, and just more generically application layer gateways. SIT is an algorithm as much as it is an actual device that basically just translates between IPv4 and IPv6 headers. It also translates ICMP messages and does things like, adds the ICMP pseudo header checksum and does all of those kinds of things internally with ICMP that's necessary to do when translating between the two. It also fragments IPv4 messages to fit the IPv6 MTU when necessary. Most of you know that with IPv6, one of the major differences from IPv4 is that routers no longer do fragmentation in IPv6. It's up to the client or the end user's device to either test MTUs, do path MTU discovery, and then fragment packets accordingly, or always send packets less than the maximum transmission unit that's allowed on IPv6. There's 2 kinds of addresses. There's an IPv4 translated address, which is used to refer to IPv6 enabled nodes. And then there's an IPv4 mapped address that refers to IPv4 only nodes. They look real similar, but you can see the syntax here. There's a 96-bit prefix shown here for IPv4 translated addresses. Then you add a 32-bit IPv4 address to that. For IPv4 mapped addresses, there's also a 96-bit prefix that's different from the translated address that you also add a 32-bit v4 address to. And as it says here, SIT requires IPv6 hosts to actually acquire an IPv4 address. Here's how this works. Here we've got a SIT device, we've got an IPv4 network, an IPv6 network, and then we've got an IPv6 host that you'll notice has both an IPv4 address in it and also a v6 address. And we've got a v4 only host up here. The host sends a packet. Here's the source address. You'll notice this is the this source address refers to this v6 only host. The destination address uses the embedded prefix that refers to the v4 only host, and you can see we've got source and destination v4 addresses embedded in that. The SIT device here simply removes these prefixes, these v6 specific prefixes, and keeps the embedded v4 prefixes to communicate out to the v4 only host. And then the same process happens the other way going back. And this is stateless. Some other things here that are shown. SIT also does translation for the class, the traffic class field to the type of service field. Traffic class in v6 to type of service in v4. Translates or adjusts the payload length fields accordingly. Translates protocol number to next header numbers. Protocol number used in v4, next header number is used in v6, and translates the TTL to hop limit. TTL, which actually is the same field, it's just renamed in v6. v6 uses a hop limit field, v4 uses a TTL, but it's functionally the same thing. But all those things are translated. Then the translator that's probably in most wide use right now is NATPT, which, unlike SIT, which is stateless, NATPT is stateful, although it still uses the SIT algorithm for doing the actual header translations and such. It's stateful in terms of tracking supported sessions, and because it is stateful, inbound and outbound session packets need to pass through the same NAT device, because that device is the one that has this stateful mapping. This is probably the biggest drawback to NAT, because all of your traffic has to pass through the same device in both directions. A couple of variations. There's basic NATPT, which just provides the translation of the v6 and v4 addresses using a pool of v4 addresses. And there's, I can never pronounce it well, but NAPT, which also does port translation. So you can manipulate the IPv6 port number so that multiple, as it says, v6 sources can share a single IPv6 address. NATPT also specifies DNS application level gateways, but there's some problems there. And given our short time, I'm not going to go into a lot of that, but most of the problems concern when DNS does not actually pass through the NAT device. If you have a DNS device on the same side as your v6 device, there can be some possible confusion. And as I've got down here, down at the very bottom, there's a couple of internet drafts. The first one talks about the problems, DNS-related problems with NATPT. And the second draft down here discusses some proposed solutions to the problems there. So if you want to know a bit more about DNS problems with NATPT, I would point you to those two drafts. Here's just the basics of how NATPT works. I think most of it's pretty predictable. You can see we've got a v6 network and a v4 network. This NATPT device has an IPv6 prefix shown here, and it also has an IPv4 pool that it assigns IPv4 addresses out of. Down here we've got a v6 host that wants to talk to a v4 host. The first thing that's going to happen is it's going to send a DNS query wanting to know what's the address of v4host.4net.org. DNS responds with an A record and this IPv4 address. NATPT takes that A record and translates it into a quad A record, a v6 quad A record, with a v6 address associated with it. And notice that this IPv4 address is now embedded in this v6 address. Then to actually communicate, now that we've got the DNS resolution, this host sends a packet out, a v6 packet, has its v6 address as the source, and that translated destination address with the embedded v4 in it. In the NAT device, we do a mapping. On the inside, we've got this source address, and on the outside, we've assigned it out of this pool up here an IPv4 address. And of course, then it just goes IPv4 normally. The v4 host responds using IPv4, and then the NAT device consults its table and replaces the numbers accordingly to get back to v6. So very much a NAT kind of functionality there, except you're also translating v4 to v6 using SIT processes. A few other translators here. There's a thing called bump in the stack, where the translator actually resides in the host. I haven't seen this work, so there's nothing much here except just an example taken from the internet draft on this. And it allows IPv6 applications to run on an IPv6 IPv4 applications to run on an IPv6 host. There's three components shown in this stack here. Of course, there's the IPv6 component. Then there's a translator above that that uses, again, SIT algorithms to translate between v4 and v6. There's also an address mapper that maintains the IPv4 address pool and maps v6 addresses to v4 addresses. And then there's the extension name resolver that takes care of the DNS queries and converts quad A records to A records and such. Moving up to a transport layer, there's a thing called a transport relay translator. This is based, you can think of this, the operation is really similar to a proxy firewall. By going to the TCP or UDP layers, it avoids any kind of translation of the network level packets themselves, because it actually terminates the sessions on the TRT box. As it shows here, there's two connections. There's the initiation to the TRT itself, and then the TRT sets up another session to the end node. It also requires some special DNS functionality. It has no DNS translation itself, so there's an assumption with TRT that DNS has been translated through some other means. Here's an example of how this works. Down here again, we've got this v6 host with some v6 address on a v6 network, of course. We've got TRT that has this dummy prefix, and it also has an IPv4 address. Out here is a v4 host on a v4 network. The v6 host has done a query to this so-called special DNS for v4, but the special DNS, rather than returning an A record, returns a quad A record that has the address, the v4 address of that host embedded in the v6. So now we just send, we start, in this case, a TCP session to the TRT with the destination of this address that was returned, wanting to go out to this host. The TRT, though, actually terminates that TCP session itself, as shown here. So the TCP session goes no further than the TRT, which then establishes a separate TCP session out to the host using v4. So you can kind of see where that's that proxy firewall kind of functionality. There's no actual packets that go directly from the v6 host to v4. It's all terminated at the TRT. Then there's bump in the API, which, as it says here, allows dual-stacked hosts, dual-stacked IPv6 hosts to use IPv4 applications. Something similar to bump in the stack that we saw earlier, but the translation is between v4 and v6 APIs. The API translator resides between the socket API module and the v4, v6 TCP IP modules. And there's no header translation required. And actually, I have no idea why I put this last thing in here, because it does header translation, and then I've just said no header translation required. It's been a while since I've read that document, and I've forgotten why I put that in there. But here's an example of bump in the API. And you can see up here you've got v4 applications. Here's the socket API. And down here, all together, is the API translator that has three parts to it. One part is the name resolver that switches between A and quad A records for the DNS calls. There's an address mapper that uses an internal pool of unassigned IP addresses, specifically in this range shown here, that maps to IPv6, and then a function mapper that actually does the socket API function translation between v4 and v6. Then there's SOCKS 64, which is based on, as you know, SOCKS is a pretty well-used security protocol. It uses the existing SOCKS version 5 protocol, described as shown here in RFC 1928, originally designed for firewalls. There's two basic components, and again, this is something I'm kind of pulling out of the internet drafts. I haven't played around with SOCKS 64 myself, so Can't speak real authoritatively about it. But there's two basic components. There's a gateway, which is a SOC server, and it terminates the v4 and v6 connections and actually does a relay, kind of like the TRT does, except now we're moving up to the application layer. And then there's the SOX lib itself, the SOX library that installs on a client between the application layer and the socket layer. And again, it also maintains a mapping table using these unassigned IP addresses and the logical host names. And here's just sort of an example of how this works. On the client with the SOX lib installed, you can see that we've got an API in here between the application layer and the socket DNS and so forth. We're talking v6 here, and we have this SOXified connection to the gateway. Both data and control information is going through here. You can see this gateway goes up through IPv6, does the necessary application translation, goes back through IPv4, and then out to some IPv4 destination out here. And that's SOX 64. And then just generically, there are application layer gateways. I had some mention earlier when I was talking about NATPT, talking about DNS application layer gateways. These are, as the name implies, application-specific translators. Needed usually when an application layer contains an IP address that needs to be translated in some way. And then moving from translators, I'm actually better on time than I thought I would be. Any questions so far? I've sort of been just going on and on here, and everybody's been really quiet. Okay. The big transition issue that I want to talk about here, kind of getting away from transition tools, is DNS. Particular issues with DNS, the big issue is namespace fragmentation. You know, if you have an IPv4 DNS and you have an IPv6 DNS, you don't want to have any kind of fragmentation of the namespace where you can't resolve to either or. But how does an IPv4 host resolve a name that belongs in the IPv6 namespace, and vice versa? And how does a dual stack host know which of these servers to query? If I have, dual stacked, my dual stack device here, if there are separate v4 and v6 DNS servers out there, and I want to go to resolve joe.cisco.com, how do I know which one of those servers to go to? These are issues that need to be resolved or contemplated with DNS. How do root servers share records with MX records? How does an IPv4 user send email to IPv6 users and vice versa? Well, solutions, the primary solution is to use a dual stack resolver. You don't not use separate v4 and v6 resolvers, so that you have a resolver that understands both. Every zone, as it shows here, as it says here, should be served by at least one v4 DNS server. You can use translators. NATPT does not work very well for this for reasons that I pointed kind of briefly to earlier. There is a proxy DNS translator called TOTD, that I haven't played around with much, but it's out there, that supposedly works better than the DNS ALG in NATPT. And some of these issues are discussed in section 3.2 of RFC 1933, if you want to see those a bit more. But what I'd really like to talk about kind of moving forward here is the two types of records that are used for IPv6. The first is a thing called a quad A record, which is described in RFC 1886. Is supported in bind 4.9 and up. The RFC actually recommends, actually I don't know if the RFC recommends it, I've seen it somewhere, but bind 8 is recommended for quad A records. And these are just a simple extension of A records, which means that there's a lot of experience out there They should be easy to understand because there's not that much of a change. And here a quad A record is shown. And if you're familiar with A records, then you certainly know this. In this case, I've got some device named Homer. It's shown that it's a quad A record, and here's the IPv6 address. And of course, the name of quad A records kind of implies the fact that the IPv6 address is 4 times as long as a v4 address in an A record. And then you also have IP6 ARPA, which is analogous to the, I can never say that in address ARPA, for reverse mapping. But that's kind of an ugly beast, which is shown here. So your PTR record using this IP6 ARPA, which I've shown this actually would return a name of homer.simpson.net down here, but it's this address written in reverse dotted hex nibbles. And this is a big, long, ugly thing, and it's kind of cumbersome to work with. There is an earlier version of this called IP6 int, but in RFC 3152, that's deprecated in favor of IP6 ARPA. But this is a quad A record, and the PTR, associated PTR records for doing reverse mapping. There's also a thing called an A6 record, which is proposed as an alternative to quad A records. It's stated on a slide a little bit later, but I'll state it now because I think it's important to hear that right away, is that just very recently, A6 records have been changed from the proposed standard to experimental status. Pretty much what was happening out in the real world is that everybody was using quad A records. So there's certainly some advantages to A6, which is why I'm going to talk about it at all. But for now, everybody's sort of just stuck with quad A records. A6 is described in RFC 2874, has a record type of 38, and the reason A6 records are interesting is because a single record can contain the entire IPv6 address, or it can contain a portion of an IPv6 address with a reference to another record that contains another portion. And you can actually chain these records together to do a lookup of an IPv6 address. And it's supported in bind 9 as it's shown here. The records are more complicated, but the advantage is that network renumbering could be much easier. And rather than kind of read through all of this, I'll show you an example on this page here of a record chain. In this case, we've got a query name of homer.simpson.net. Well, the first thing you do is go to a DNS server and you look up simpson.net and you look up Homer, the record for Homer here. It shows that this is an A6 record. This number right here says that I'm going to return a portion of that address, and there are 64 bits ahead of this address chunk that still need to be found. So basically, what gets returned here is just the interface ID for this device, Homer. And you have a reference to another record, SLA5, which is at subnets.simpson.net. So we go to subnets.simpson.net, we find the record for SLA5, we get another chunk of the address. And this says that there are another 48 bits to be found. And they can be found at site3.sites.net. We go to sites.net, look for site 3 record. We get the next chunk. We still need 32 bits. We go to area 10. Here's areas.net and area 10. We get the next chunk. 24 bits remain, which we can find in a record called TLA1 at tlas.net. Here at tlas.net, we have TLA1. No bits remaining because this is our last 24 bits. And now, if we put all that stuff together, we've got the returned address. Why that's useful is this. If you're doing a network renumbering, maybe the only thing that really needs to be renumbered in your network is the TLA portion, or maybe the TLA and some portion after that. You can actually renumber your network in the DNS records by just changing just this portion of the record rather than having to change every record for every device in the DNS. That's what the advantage of A6 is. The disadvantage is probably kind of obvious to you too, that rather than looking at a single record, we're having to look through a chain of records, which means, and these records could be on different DNS servers, which means it takes a lot longer to do the name resolution using A6. That's really the big drawback to A6 records, is that it's going to take a long time to do a name resolution. Another piece that goes along with this is DNAME, which is described in RFC 2672, and kind of running out of time here, so just going through this really quickly. DNAME provides this chaining of records just like A6 records does, so it's sort of a counterpart to A6 for doing reverse lookups. And like A6, it was in RFC 3363 was changed from a proposed standard to experimental status, so we won't look at it very long. There's also a thing called bit string labels that's important with DNS and for breaking up these records. Bit string labels for IPv6 are described in RFC 2673. An example is shown here. We've got an IPv6 address which could be represented this way using a bit string label, or you can actually break the thing up as shown here, which allows you to again do chains. And the advantage, kind of already said that, it's more compact than the IP6 int or IP6, the textual representation that we saw earlier. But all resolvers and authoritative servers need to be upgraded before that label type can be used. And here's the DNAME reverse lookup. In this case, we query this address here, and you can see, using these bitstring labels, that we have kind of the same thing that happened with A6 records. You get a piece of the address and a reference to the next record, and as you go through this chain at the end, you get enough information that now you've hit this homer.simpson.net and you get the returned name there. So, Quad A or A6? Well, as I said, it's something of a moot point right now because A6 has been relegated to experimental status. There is a good discussion of the trade-offs in RFC 3364. The advantages of Quad A records is that they are essentially identical to A records, which means there is a lot of practical experience with them. People understand Quad A records and know how to work with them. They're optimized, as it says here, kind of in quotes, I took this from the RFC, it's optimized for read, which means you get very fast, or relatively fast, returns of a DNS name lookup with Quad A because you only look at a single record. The disadvantage is that it's difficult to inject new data. If you want to do a network renumbering, you've got to change all of your records. A6, the pros here, and again I've got this in quotes because I took it out of the RFC, it's optimized for write. In other words, it's very easy to change records. And could be superior for rapid renumbering and so forth, and could have some implications for some multi-homing approaches. Unfortunately, I don't have the multi-homing section in here anymore. The cons, the long chains, as I already mentioned, can reduce performance, and there's not much operational experience with that. As a result, Quad A is the preferred DNS method right now for production deployment. And I think we're down to the last slide here, which is pretty, I actually got that almost right on time. Some open or semi-open issues with IPv6 and transitioning to IPv6. One is security. End-to-end security, as I mentioned back at the very beginning of this talk, is better than trying to hide behind a NAT, which is kind of a broken way of doing security. So IPv6 gives us the opportunity to improve the present state of security on the internet, which is pretty horrendous. Firewalls really need to become smarter, and this really is kind of aside from IPv6. They need to become smarter whether we're talking about IPv6 or IPv4. There are too many hacks with firewalls right now that application developers use and so forth. Firewalls need to start learning how to examine things better. Transition vulnerabilities need to be better understood. And unfortunately, the only way those vulnerabilities are probably going to be understood is to start doing transitions. Particularly, security vulnerabilities need to be better understood. There are documents out there, some internet drafts that discuss potentials for abuse and denial of service attacks of different kinds of IPv6 addresses used in various transition technologies. Management definitely needs to be improved. There was a statement just this morning, in fact you made it, that the MIBs for IPv6 in routers are not as good as the MIBs for IPv4. That needs to improve. And that's something that got to go back on the shoulder of router vendors, among other things. And the IPv6 network itself needs to be managed in conjunction with IPv4. You shouldn't have to have separate management platforms or somehow view the IPv6 portion of your network separately from IPv4. What I've heard over and over from various operators is, I need to see my network as a whole, and the management platforms that I use need to give me that visibility, and I should be able to manage and view my IPv6 traffic in the same way I can IPv4. In the long term, IPv6 networks should actually be cheaper to manage than IPv4 networks. Part of that could have to do with end-to-end security. A big part of that can have to do with getting rid of NATs and dynamic IP address pools and that sort of thing. Multi-homing is a big issue. There's nothing inherent in IPv6 that improves the really crummy state that we're in right now with the internet with IPv4 multi-homing and the kind of not so good practices that we've had with IPv4 multi-homing of leaking long addresses into the default free zone and all of that kind of thing. What IPv6 transition does is give us an opportunity to fix the things that we've done wrong in IPv4. Because if we're going to transition anyway, as we start, why not try doing better multi-homing practices? As I said earlier, on the with these slides posted on the net, I've actually put the multi-homing portion of this presentation at the very end of this presentation so you can look at it. And I'll try to do a multi-homing presentation in Chicago because there's some important issues there. There are a lot of proposed solutions right now for multi-homing for IPv6. None of them are perfect. There's certainly plenty of ground and plenty of room for intelligent people to come up with better solutions for multi-homing, because there's only going to be a limited amount of time where we can fix that. Already, people running some IPv6 networks are talking about just using IPv4 types of multi-homing procedures because there's nothing better to be done out there. Another issue is that very much PI address space is needed for IPv6. Right now, with IPv6, if you're allocated, if you're way down the chain somewhere, you're going to get a PA address space. That's a big turnoff for a lot of enterprises. Enterprises will say, I want a PI address space for multi-homing and such, so that I'm not dependent on any one provider. And there's discussion about that, but that's something that's needed. And then finally, it sounds kind of funny to say it in this venue, but marketing is needed. There are a lot of misconceptions and myths out there still around IPv6. I mentioned a couple of those back at the very beginning of the talk, and I've kind of put that in here as a come on to say, if you're not involved, if you're interested and you're not involved with the IPv6 forum, which is mainly its main task is to market IPv6. We could certainly use your help writing articles, particularly speaking and trying to kill off these myriad myths and get some reality around what transitioning to IPv6 is all about. And with that, are there any questions? Wow. I just educated you so well, there's not anything else you need to know, is it? Somehow I doubt that. If you think of some questions later, my email address is on here. I'm just jeff@juniper.net, and please feel free to email me at any time. Question? Oh, yeah.
One quick question.
Sure.
Common practice in IPv6 period is the use of /126 chunks of address space with the point-to-point. There has been a internet draft published on why that is a very bad thing to do. Thus far, nobody we hear with has thought that they shared diddly about that and said they're going to use 126s, go away otherwise.
Yeah.
I personally, looking at that, can't see the likelihood of any cast address in a point-to-point carrying relationship being terribly useful down the road.
Yeah.
Do you think there's any real reason not to use 126?
I can't think of any. Do you have any thoughts on that?
You know, it would just be the HCAS issue, and you know, we use /16 for some reason, but I'm not sure there was a group of information. You know,
Yeah.
if you look at the HCAS issue, it said, well, you know, it's there. The 127 or 126 still kind of escape the HCAS issue.
Yeah.
Not a good answer.
Yeah, there's.
The lack of HCAS, I think, complicates.
Yeah, I lean very much to your opinion. There's a lot of things out there, like talking about a home user gets assigned to /48, which gives you capability of like 65,000 subnets in your home. That's just sure, there's an abundant amount of IPv6 address space out there, but why be wasteful? So I don't know. I think there's some odd practices right now. Yes, sir.
So when it comes to doing DNS, my DNS guy said, I don't understand this stuff. Just tell me what to put to my DNS server, and I'll do it for you. I'll put anything.
Mm-hmm.
And I look at like an example record or a reverse pointer that uses the IPv6 adder, I guess.
Uh-huh.
And obviously, you're not going to figure that out with a calculator or something. I assume there's tools that are readily available to help your DNS maintainer stay sane with that kind of stuff.
I don't know. I would assume so. Not being a DNS guy, like I said, I'm a router guy, and so I actually. Do you know if there's any automated DNS tools for IPv6 right now?
I wrote a 2-minute Perl script to do handle the inverse translation issue. I mean, that's fairly trivial. It's just got to be smart to understand what double colons mean, and that's about it.
So it's an easy thing to do.
Of course, flip it around and put it out with all the dots, and you cut and paste it. That's not clean. It'd be nice to internalize and make it a filter, but I was lazy and I just wanted it to work.
What about the various commercial tools that are available? Do you know if any of those will deal with IPv6?
It's a protocol name server, and it does it automatically.
Okay.
It understands.
So there is stuff available.
Full DNS product. That's not. It's fairly pricey. It's fine for enterprise-wide DNS.
Yeah, but he has a lot of money. He does. That's all right.
Okay. Right. It's also finished, so if you have to buy American, that doesn't work. But.
Okay. Other questions? Thought I saw another hand somewhere. Over here? Anything? Okay. Well, thank you very much for coming and for putting up with me for an hour and a half. And like I said, if questions occur to you later, please feel free to email me. I'm always happy to hear from anybody. If I can't answer the question, I can certainly point you to someone who can. Thanks a lot.